Okay, welcome to the lecture number 12 of Irrigation Drainage series. So, in this lecture we are going to learn irrigation channel design. So, in the previous lecture we focused mostly on canal irrigation conveyance and also the structures and lining and other things. So, here how to design that particular channel. Okay. So, this we are going to see. So, basically these irrigation channels are either trapezoidal or rectangular, or sometimes you may see the circular. So, the main parameters here we are talking about the design part. So, one is the top width, freeboard. Okay, so, the top width, freeboard and channel bed, the slope, wetted perimeter and hydraulic radius are equal to A by P. So, the wetted perimeter, suppose you have, so this is the trapezoidal channel, okay, your water surface is lying on top. Okay. So, your wetted perimeter will be this plus this plus this. Okay. So, only the wetted part. Okay. So, in case of circular, so if this is the water surface. So, from this point to this point is the, so from this point to this point is the wetted perimeter. Okay. So, then so here, so hydraulic radius which is the area divided by wetted perimeter. So, that is hydraulic radius. So, these components we are mainly focusing in the design of irrigation channel. So, this picture clearly shows the flow depth and channel bed, or channel bed and channel, this is the channel top. Okay. So, then this is the slope. So, this is the vertical and horizontal component of slope. So, there is a freeboard. So, this is for factor of safety. So, you need to maintain the freeboard for each irrigation channel. Okay. So, here so the next is the open channel flow. So, basically the two principles or two equations are we need to consider. One is the Chase's equation and Manning's equation. So, these equations are, so in Chase, so he has come up with this equation long back. I mean, this is the oldest equation. Then after that, Manning's, after doing certain experiments, so he found, he just modified the Chase's equation. So, that is V 1 by n r power 2 by 3 s power half. So, in both cases, so C the Chase's constant and Manning's n. So, they have a relationship r power 1 by 6. So, C is equal to r power 1 by 6 by n. Okay. So, in this equation, so V is the velocity of flow. Okay. And then R hydraulic radius flow section, S is the channel slope in meter per meter, and Chase's constant C and Manning's n. Okay. So, or Manning's roughness coefficient. So, okay. So, here some channels, some material used in the channels and their n value. So, concrete, stone masonry, soil cement, bare soil and vegetable waterways. So, vegetable waterways relatively give larger roughness compared to other structures. So, that is why if you see n value is more compared to other channel types. Okay. So, these two equations are very important when you are designing the irrigation channels. So, here how to estimate the maximum discharge through rectangular channels, because that is we are looking for, it is more economical also. So, our intention is to carry maximum flow, right, in irrigation channels. So, that is the reason you have to find out in which condition you achieve the maximum flow in the particular structure channel. So, here for that there are some steps involved to find out the maximum discharge condition. in a particular channel, it should be a rectangular or trapezoidal. So, for example, in case of rectangular channel, so this is a rectangular channel which has width b and depth d, and of course, there is a free board. So, based on this, in what condition you achieve the maximum discharge in this particular channel, so that we can design the b and d, I mean we can determine b and d values. Okay. So, basically in this case from this graph, area which is equal to b into d, because rectangular. So, rectangular area which is equal to breadth into depth. So, then the discharge is equal to area multiplied by velocity. So, and putting the Chase's velocity equation here, area into Chase's velocity equation c square root of r s. So, and that is the q value, and then wetted perimeter p. So, as I said, wetted perimeter is the sum of this plus this plus this. Okay. So, that is b plus d plus another d. Okay. This is the d. So, d plus b plus d. So, altogether you get b plus 2d, right. So, then wetted perimeter p is equal to, right. So, a, so here what I did, so you just convert b from here. So, bring a b d into, so b can be, so from here this equation b is equal to a by d. So, substitute for b, that a by d plus 2d. So, this is p is equal to a by d plus 2d. Then, so for in your case, the wetted parameter needs to be maximized. Okay. So, when the wetted parameter is maximum, you expect maximum discharge. Okay. So, that is dp by dd. So, wetted parameter with respect to depth, needs to be maximum. So, for that you have to differentiate the wetted parameter with respect to d. So, then when you differentiate this equation dp by dd, so this is minus a by d square plus 2, which is equal to 0, or a by d square equal to 2, or a is equal to 2d square, or b is and or b is equal to 2d, because a is b into d. Okay. So, here you got, because a substitute, this is b into d is equal to 2d square, and then b is equal to 2d. Okay. So, that means the breadth or the width should be 2 times the depth. So, this is the, in which in this case you get maximum wetted perimeter. Okay, this is one condition. Then the hydraulic radius r, which is equal to a by p, a is bd and p is b plus 2d, and substitute b as 2d, because here this is the maximum case you got, right, b is equal to 2d. So, substitute it here and then substitute it here, okay, and then 2d square by 4d, you get d by 2. Okay. So, the maximum discharge conditions are b is equal to 2d and r is equal to d by 2. So, these are the two conditions you need to consider while constructing or designing a rectangular channel for getting the maximum discharge through the rectangular channel. So, and then the next part is, so what about the maximum discharge in case of trapezoidal channels, that is the maximum in case of rectangular channel, and this is the trapezoidal channel where the slope is, so where you get the slope is 1 is, sorry, not this, so 1 is to z. Okay. So, I am sorry. Okay. So, 1 is z, that means 1 vertical and z horizontal. So, that is the slope. So, here we will follow the similar steps as in case of rectangular channel. So, area A is equal to B into B into D plus 2 half into D into ZD. So, how do you get this? So, here in order to get area, just make so this is one triangle and this is another triangle. So, one triangle, second triangle and this is third. So, combining these three you will get the area of cross section. So, the first one is D into B. So, this is D. So, D into B. So, that is this part, okay. And then half D into ZD. So, there are two triangles, that is why they 2. So, two triangles. So, let us find out the area of one triangle. So, that is half into, so D, this is the thickness or depth. So, you need to find out what is this base. So, that base, so see since this is 1 into Z, so that means so Z into D. So, it's 1 when it is 1 it is a Z, when it is D, Z into D. So, Z into D. Okay. So, that is why half D into Z into D, because there are two triangles 2. So, this is the total area of cross section, and then if you can simplify that BD into ZD square, then take D out or A by D, right. So, take D out. So, that is A by D, which is equal to B plus ZD, or B is equal to A by D minus ZD. Okay. So, and then discharge the same step Q into A into V. So, you change this velocity equation and you end up with this term, and P, this is wetted perimeter. So, for wetted perimeter, so this length plus this length plus this length. Okay. So, this length is given B, okay. And again these two are equal. So, once you know the length of this, and you can multiply with 2. Okay. So, this 2. So, length of this will be, this is a this is the triangle. Okay. So, the triangle has 3 sides, I said. So, this side has ZD, okay, is already we know, and this is D. So, in order to find out this side, so ZD square plus D square the whole square. Okay. So, that is what we got here, Z square D square plus D square, and since there are two sides 2, and this is after simplification. So, P is equal to this much. So, P will be minimum when dP by BD is equal to 0. Okay. So, dP by dd is equal to 0, dP by dd which is equal. So, you have to differentiate this. So, once you differentiate, you get A by d square plus z minus 2 z square plus 1 equal to 0, and then after simplification, okay, after simplification you get this, or b plus 2 z d by 2 equal to d into d square root of z square plus 1. Okay. So, here if you see again dP by dd, differentiating p with respect to d, and so here a by minus a by d square minus z, good, and 2 d gets 1 and z square plus 1, or then if you simplify that, this is an equation, and finally you end up with this equation. Okay. So, then next is, so next is, so this is the previous step, this is the previous step. So, in case of hydraulic radius, so R is equal to A by P. Okay. So, A you got this, okay, P, so B plus 2D z square plus, this is from previous equation, and then once you divide this, So, d plus b plus z d, b plus 2 z d. Okay, so, here from here if you bring it down here, right. So, b plus I mean this is equal to 2 d plus z square plus 1 is equal to b plus 2 z d. Okay. So, then d b plus z d by 2 b plus z d, which is equal to, so this gets cancels out, and finally, d by 2. So, for maximum discharge or maximum velocity, so you get b plus 2 z d by 2, okay, here, which is equal to, this is the top width. So, top width has, right. So, this is b plus, so this side plus this side. So, that is what you get, b plus 2 z d by 2, this is the top width, okay, 2 z d, this is z d and this is also z d. So, b plus 2 z d is the top width. So, that is the top width divided by 2 is equal to d square root z plus 1, the same thing. So, the sloping side is equal to half of the top width. Okay. So, this is the maximum conditions. So, one condition is, see, the sloping side is equal to half of the top width, and hydraulic radius is half of the flow depth. This is another the previously we got this. So, the two conditions you have to satisfy in order to get the maximum discharge. Okay. Okay, here the example, the first example shows the determine the velocity of flow and discharge capacity of unlined canal branch of a grade of 1 meter in 800 meter, having depth of 1.5 meter, bottom width 0.8 meter and side slope 1:1. Okay. So, this given data, if you see, depth of flow is given, bed width is given b, canal bottom s 1/800 and then side slope. Okay. So, the velocity of flow, so first of all find out the area. So, I mean you use the Manning's roughness coefficient n is equal to 0.023 for what is this unlined canal, this is for unlined canal. Okay. And for area, this is a formula, this is a trapezoidal channel, suppose this is a trapezoidal channel. Okay. So, B, D, this is 1:1, right, 1:1. So, this is also would be D. Okay. So, BDD. So, ZD square. Okay. So, then substituting the values you get the area 3.45 meter square. Similarly, wetted perimeter, substitute all the values, you get wetted perimeter this much. Hydraulic radius A by P, once you get A and P, A by P, so that is hydraulic radius. Now, velocity, this is Manning's N equation. So, substitute, of course, this is a capital N. Substitute the values. So, you have R value, you have S value, you have N value, and finally, you get 1.193 meter per second, and the discharge Q, that is A into V. So, A is so this is A, and velocity 1.19. So, the finally you get 4.116 meter cube per second. Okay, so another example here. So, attention trapezoidal section, this is trapezoidal section, following conditions. So, discharge is given, slope is given, side slopes and Manning's N is given. Okay. So, this is a capital N, let us say. So, design earthen channel. So, find out the dimensions of the earthen channel. So, for most economical trapezoidal section, right. So, in the previous equation if you recall, so, these two conditions we derived. One is the top width by 2, this is the top width, is equal to d into square root of z square plus 1, or hydraulic radius, which is d by 2. So, bringing this here, b plus 2gz or b plus 2.6 d, b plus 2, because the z value is given, right. So, z is given 1.3 multiplied by 2, you get 2.6 d, 2d into 1.3 is equal. So, substitute the value, see here d value. So, d is Manning's roughness coefficient. So, b or b plus 2d is equal to, so all are having d value and b plus d. Okay. So, from this b is in terms of 0.68 into d. So, b is a function of d. Now, area A is equal to d into b plus zd. So, this is also we derived, and substitute the values of b and z, and A is equal to 1.98 d square. Now, discharge q A into V, right. So, putting the values, you get this equation, okay. And then from this equation, so and then you can solve that equation. So, finally, you get d is equal to 1.04 meter, and then substitute in the previous equations, you get b is equal to 0.7072. If you assume 20% free bore of flow depth, so the depth of channel will be 1.04 into 1.20, because this is 100% plus 20%, 120%, right. So, 1.20, 1.25 is the depth of the channel including the free bore, and top width is b plus 2z dc, this is small c. So, then you will get 3.957. So, finally, the dimensions of the channel. So, d flow depth, depth of channel, top width and side slopes. Okay. So, this way you have to design the channel. Okay. So, then pipe flow irrigation water. So, mostly for pipe flow, the equations we use describes the fluid flow are based on 3 fundamental law of physics. So, one is conservation of matter or mass, so which states that matter cannot be created or destroyed, but can be converted by a chemical process. Okay. So, matter cannot be created or destroyed, but can be converted. And conservation of energy. So, energy cannot be created or destroyed, but it can be converted from one type to another. Okay. For example, potential to kinetic energy. So, and then conservation of momentum. So, a moving body cannot gain or lose momentum unless an external force acts on it. This is a conservation of momentum. So, the momentum, suppose you're sitting on a bus, right. So, you are traveling in a bus, and all of a sudden there is a brake. So, because you are initially moving with the same velocity of the bus, then all of a sudden stopped, right. So, and then you are not going to travel even the bus stop. So, you are going to stop, but all of a sudden you are going to fall, right. Bus can stop, but you are going to fall, because there is you are under momentum in the bus. So, okay. So, moving body cannot gain or lose momentum unless external force acts upon it. Okay. And a theories of hydraulics and fluid flows, they are Pascal's law and continuity equation or conservation of mass, or Bernoulli's equation or energy equation. Okay. So, these theories are going to use in fluid flow. So, the next is hydraulic and energy grade lines for pipe flow. So, when the water is fully flowing in pipes, right. So, there are 2 lines basically, one is the hydraulic gradient line, right, hydraulic gradient line, the other one is energy line. So, these 2 lines. So, when there is a smooth flow or laminar flow and no friction loss, then the hydraulic gradient line may be maybe may be equal to the energy gradient line. Okay. The total energy line, which is hydraulic gradient line and types of flow in pipes Reynolds number, is very important, which is defined as rho V d by mu, where rho is the density of fluid and V is the mean velocity and d is the diameter of the pipe and mu the coefficient of viscosity of the fluid. Okay. And once you put the values, if the value is less than 2100, then we call a laminar flow, and transition flow 2100 to 4000, and more than 4000 is called turbulent flow. So, here the friction head loss is very important when you are talking about the total head loss. So, the total head loss here, so Z from the datum, and this is elevation, okay, and this is the pressure, sorry, this is the pressure head, and this is velocity head, and this is the friction head. So, the total head includes the elevation head, pressure head, velocity head, and friction head. Okay. All right. So, hydraulics, again velocity profile, if you are looking in a pipe. So, in the middle it is the maximum, okay. The velocity is maximum in the middle, and the ends, I mean at the surface of the pipe. So, the velocity will be minimum because of the friction, right. This is kind of a string. Suppose you are holding a string and the water is flowing, okay. So, since you are holding here, right, so it is not going to sag, but in the middle is going to sag. So, here the velocity is less because there is the friction force which is acting on the surface here, right. So, here the friction is less, I mean, so that is why you get this kind of. How about open channel? Open channel, the same thing, but you are going to have the velocity less velocity in bottom and more velocity in top. Okay. See, this is the open channel flow. Okay. So, then head loss in pipe flow. So, major head loss is the friction, and minor head loss is change in diameter or change in velocity in bends, joints, walls, and similar items. So, these are the minor ones. So, Darcy-Weisbach equation, so will be used to find out the head loss, friction head loss mostly, that is capital F is small h f, the friction head loss, which is equal to F L V square by 2 Z D. Okay. So, L is the length of pipe, velocity in the pipe, F is the friction factor, okay, and D diameter of the pipe, acceleration due to gravity. So, here the example determined the head loss due to friction in an irrigation pipe having 150 meter long and 25 centimeter diameter, and the velocity flowing water in the pipe is 2. Okay. So, here this is 2 meter per second, let us say. So, head loss according to Darcy-Weisbach equation, that is H f is equal to F L V square by 2 G D or D into 2 Z, and velocity is given. So, this assume F is equal to 0.025, H f substituting the values you get 3.058 meter of water, and you can also use the friction tables, right, from the table. So, the table gives the friction head loss by knowing the discharge, knowing the discharge and diameter and for 100 meter length you get H f, and you can, so based on the given length you can reduce and you can estimate the corresponding H f for the particular length. Okay. Okay, so here there is a section size should be based on the following. So, hydraulic capacity required, pipe size, and pipe size is very important in irrigation water flow. So, what are the main pipes for parameters needs to be calculated in case of finding out the size of the pipe. So, for hydraulic capacity, head loss and economy. So, pipe size is based on hydraulic capacity, that is A is equal to Q by V. So, since Q A is equal to pi by 4 d square, and substitute it here, you get diameter, Q discharge and V permissible velocity. Okay. Okay, so or the same thing. Yeah, so here an example of finding out the parameters of size of the pipe. So, compute the size of best quality cast iron pipe it will carry. So, this is the discharge with head loss 2 meter per 1000 meter. So, use the same equation. So, find out this is given, Q is given. So, L is given, HF is given. So, and V find out, right. So, substitute the values, you get d power 5 is this much, and find out d value. So, d is 44.15 centimeter. The pipe diameter is 44.15 centimeter or 44 centimeter, let us say. Okay. So, this is the pipe size. So, the next is, so whatever we talked earlier is on irrigation scheduling we are talking. So, that is on form level. So, and also similarly we do the schedule at the irrigation canal level. Okay. So, this is called canal irrigation scheduling. So, canal irrigation scheduling, so basically the aim is to provide irrigation water at the right time, right amount and right place. Okay. So, whereas in on form, so the irrigation scheduling basically, as I said, the 3 components. So, when to give irrigation, how much to give irrigation and how to give irrigation, that is the form level. Whereas in canal case, so we have to look for the right time and right amount. Okay. So, this is similar, and right place, right. So, these 3 are important for the canal systems. So, canal scheduling types, how to release water at the canal level, that is rigid schedules and flexible schedules. So, rigid means the time is fixed for a particular season. So, we will give water on this particular month or this particular day or this particular hour, right. Whereas, the flexible scheduling case, so this is basically the demand, based on the demand we are going to change the dates or amount, right, anything. So, let us see what are the types of these schedulings, canal schedulings, and which part of India is really practicing these schedules. So, rigid schedule, there is a difference between rigid and flexible scheduling. So, rigid scheduling, the canal is operated continuously at a constant flow rate. Okay. So, water supply is desired when flexible in frequency or rate or duration. So, this is the another difference. So, then flow rate generally 15 to 30 liter per second, frequencies could be 7 to 14 days, right. So, for 7 days or 14 days, and durations could be 8, like 8 hours, 12 hours, 24 hours, right, kind of fixed. This is that is why this is a rigid schedule, and relatively low capital investment, right. So, since it is already predefined flow rates and predefined supply times and everything. So, very less, relatively less capital investment, and cause improper timing, excess irrigation, runoff. So, this is the main drawback in this system. So, since you are not noticing the demand, you are supplying with a constant rate and constant time and specific time. So, sometimes it is not you are releasing water, it may not be utilized by the farmer at the farm level. and low water efficiency. That is the main reason you have a low water efficiency. So, whereas flexible control, the schedules are expensive because you have to modify the schedules and instruct the stakeholders, and so it takes, it's a little expensive. Optimizing the farming operations and maintaining sustainable irrigated agriculture, and large irrigation systems are available to irrigate each crop when needed. Okay. So, since it is demand based, sometimes you have unexpected demand, so you need to cope with that. Okay. So, and the next is, so there are several irrigation canal irrigation schedulings available in India. So, it is already in practice. So, the first one is Varabandi. So, Vara means turn, Bandi means fixation. So, the turning is fixed, okay, the fixation based on some fixation. So, water distribution is performed by turns based on the predefined or irrigation schedule. That is why this is a rigid scheduling model, Varabandi. The upper tier is operated by state agency. So, here if you see, this is river, from there the main canal and branch canal and then distributory. So, from the distributory you get water to the field. So, here whatever the dotted lines are operated, managed by farmers. Okay. So, whereas the other things are owned by or managed by state agencies. Okay. So, so that is why the upper tier is operated by state agency, the lower tier is managed by farmers, right. So, general social acceptance, it has a greater social acceptance because mostly the farmers involved and the fixed what you call this water is coming, whether you require water or not, there is always water, and the main limitation is equitable distribution of water to tail and farmer is not possible due to seepage losses in the serving. So, at the tail end, sometimes what happen, the farmer at the tail end may not receive water because of the seepage losses. Okay. So, then next is Sage Pali. So, Sage Pali is another irrigation scheduling method. This is also rigid scheduling. This is practiced in Maharashtra and Gujarat. Priority is given to the tail end farmers. So, in the previous Varabandi case, the head and tailers are farmers are given the priority, whereas Sage Pali is little opposite to that. So, first the tail end farmers are given water and then serve the head end farmers and solve the tail end problem in case of Varabandi, and farmer is required to apply irrigation water right for the particular crop over a particular area each season. So, farmer every time he has to apply for the water rights. Okay. Main limitation is this tail end deprivation which is result due to the inequality water supply between head end and tail end farmers. Okay. So, this is the main drawback, and the other system is the block system. So, the block system, in case of block system what happened, this is mostly practiced western Maharashtra. State enters into 6 to 12 year agreement with the group of farmers to provide fixed quantity of water for a particular crop pattern. So, before that so around 6 to 12 years agreement will be between state agency and the farmers. So, then after that started the particular block is given water. Okay. So, the farmers in the block are required to pay for the volume of water delivered as measured by the irrigation agency. So, that particular farmers belong to that block needs to pay the irrigation cost. The block system is also devised to encourage investment in sugar. So, because sugar belt needs water. So, this is since this is water. So, since there is a water in the canal, so canal water can be used by raising sugar crop, sugar cane. So, then that is why block system is very famous in case of Maharashtra, western Maharashtra belt. Okay, so then other schedulings are assured irrigation. So, assured irrigation is a rigid scheduling. So, here what happens, some group of farmers are assured irrigation. So, till the last watering. Okay. So, then the remaining will be kind of extra water is allotted to the probable irrigation area within the system. Okay. So, the assured irrigation area farmers are billed each season, whereas the probable irrigation area are billed following their application for water. Okay. So, here this, since it is the fixed, you have to pay the assured irrigation area farmers. So, as usual, whereas the probable irrigation area, so based on their requirements, the utility of water, so they have to pay. And the other one is land classification. So, this practice state of Bihar and the southern states of Tamil Nadu and Kerala, the surface irrigation water is allocated according to the land classes. Okay. So, you have different land classes like paddy or other land classes. So, based on that the irrigation water is allotted. So, entire land in irrigation command area is classified with regards right to irrigation water. Certain key aspects of operating irrigation schedules are decided at the meeting their district collector. So, before starting the season, so there is a meeting with the district collector and they decide which crops are required in a lot of water, or which crops are required priority. Okay. Okay, so this is all about the irrigation channel design. Okay. Irrigation channel is canal design. So, in this class we were focusing on what are the design parameters, right, what are the economic design, and what is the maximum discharge condition we can arise or attain when there is a rectangular channel or trapezoidal channels. Okay. So, then how to design a pipe diameter or pipe size based on the flow condition. Okay. So, then after that we solved some examples, right. So, then similar to the farm irrigation scheduling, there is a canal irrigation scheduling. Okay. So, basically the canal irrigation scheduling is classified in two types. One is rigid scheduling, okay. The other one is flexible scheduling. So, most prominent rigid scheduling is the Warabandi. So, where the water is given to the farmers or tailends at a particular rate constantly for the pre-decided time intervals, whereas a flexible case it is I mean based on the demand you are going to revise the irrigation dates and also discharge rate. Okay. So, so with this introduction, with this the background, I mean the canal conveyance as well as the canal I mean channel design I think we completed. In the next class we will be focusing more on water measurement and also some examples, water measurement in the sense open channel as well as pipe flow case and some examples. And finally, the tutorial class will focus on the examples related to gate examinations. Okay. Thank you so much.